In the last lecture, we looked at one-way ANOVA, where there was only one categorical input to our system, and we saw some basic examples and theory of that subject. In this module, we are going to take a closer look at the same model, and we will see various implications of that model in terms of estimability and identifiability. One-way ANOVA part 2. Recap. We know that the one-way ANOVA model is written as Yij equals mu plus tau I plus epsilon ij. Here j goes from 1 to n and I goes from 1 to capital I, where capital I is the number of groups which we are comparing the means of. We can perform analysis of variance using the AOV function in R. Let us look at an example. A random sample of students in each row of a classroom was taken, and we wish to test whether the mean score of students from each row, front, middle and back, were significantly different. The R code to perform ANOVA is as follows. I am not reading out the entire code as it is difficult to follow, so just carefully read them line by line. The first line creates the data set, the second line renames the factors, the third line creates a data frame, the fourth line creates the ANOVA table, and the last line prints it. We can see from the ANOVA table that the p-value equals 0.0093, thus the test is significant at alpha equal to 0.05, arrow not all mean scores are the same. We have calculated a p-value and performed the ANOVA test. Since we found a significant result, we need to determine which group is actually different from the rest. There are several tests of statistical significance designed specifically for multiple tests. We can choose contrast to test or perform multiple comparisons. We can also find the confidence interval for each mean mu y to show which ones are significantly different from the others. Contrasts can be used only when there are clear expectations before starting an experiment, and these are reflected in the statistical experiment. Contrasts are planned comparisons. Multiple comparisons are used to perform pairwise tests of significance to test which pair of mean is significantly different. When an experiment is designed to test a specific hypothesis that some treatments are different from other treatments, we can use contrasts to test for significant differences between these specific treatments. Contrasts are more powerful than multiple comparisons because they are more specific. They are more able to pick up a significant difference. You can use a t-test on the contrast or calculate a t-confidence interval. The results are valid regardless of the results of your multiple sample ANOVA test. You are still testing a valid hypothesis. Contrast. A contrast is a combination of population means of the form psi equal to summation ai mu y, where the coefficients ai have sum 0. The corresponding sample contrast is summation ai x I bar. The standard error of this is SEC equal to the given formula. Hypothesis. To test the null hypothesis H naught equal to 0, use the test statistic T equal to C by ACC with degrees of freedom DFE that is associated with SP. The alternative hypothesis can be one or two-sided. Hypothesis. A level C confidence interval for the difference is C plus minus T times ACC, where T star is the critical value defining the middle C. Combined contrast hypothesis. H naught mu1 equal to mu2 plus mu3 plus mu4 by 3 versus HA mu1 greater than the same quantity. This is a one-tail test. Contrast coefficients are 1, 1/3, 1/3, 1/3 or 3, 1, 1, 1. Okay, now let us take a look at an example to see how to use a statistical software for testing contrast. Now, while many of these computations can be done very easily by hand for small data sets, most practical data sets are much larger, and as a result they require use of dedicated statistical software. And one such software that we are using in this module is called R, which is available for free. To see the use of R in testing contrast, we first need to have a data set. For example, the nematode data set that we had seen earlier. What we want to test here are all pairwise contrasts. Let us clearly understand what is meant by testing all pairwise contrasts. In this case, suppose we have got k different groups. Let me call them group 1, group 2 up to group k. Then we are interested in knowing whether group 1 differs from the rest. That is, I will compare group 1 with group 2, then separately group 1 with group 3, group 1 with group 4, etc., all the way up to group 1 with group k. So, I have tested k minus 1 contrasts. Now, I repeat the same thing starting with group 2. Group 2 has already been compared with group 1, we do not need to do it again. Group 2 with group 2, of course meaningless. So, we start group 2 with group 3, group 2 with group 4 and so on. So, now we have k minus 2 contrasts. Continuing like this, the very last contrast that we are going to test for will be group k minus 1 with group k. So, the total number of contrasts that we are testing is equal to k minus 1 plus k minus 2 plus dot dot dot, decreasing one by one all the way up to just 1. Simple algebra will tell you that the total number of contrasts is k times k minus 1 by 2 or k choose 2. We are going to use the function 2key HSD in R to test all these k choose 2 contrasts using a single line of code. The use of this function is quite simple. After performing the ANOVA, we have to pass the output of that ANOVA to the function 2key HSD, and it will extract all the required contrasts and test them. So, here is the R code. Let us clearly understand the different steps. The first line is response assigned to C and the list of the data values. As we know by now, C is the R function for producing a vector. So, we are basically making a vector of all the observed values. The first component is 10.8, the next is 9.1, going on all the way up to the last one, which happens to be 7.5. And then we create the treatments. These are nothing but the various groups. The groups in this case are called factors, and they are created as C rep 004, then rep 1004, rep 5004 and rep 10,004. What does that mean? Rep 04 means repeat the string 0 4 times. So, we have 0, 0, 0, 0. Follow it up with the string 1000 4 times. So, now we have a total length of 8. First 4 entries 0, the next 4 entries 1000. Follow that up with 4 5000s and 4 10,000s. So, now you have an entire vector of length 4 times 4, that is 16. So, these are the values of x, and we already have the values of y stored in the vector response. So, just bunch them up together to create a data frame which we call nematode. This is accomplished by using the function data.frame. The first column is response, the second column being treat. Now that we have created the data set, it is time to perform analysis of variance, and we already know that the function to compute analysis of variance in R is called AOV. So, we give the command ANOVA assigned AOV response tilde trait, comma data equals nematode. Response tilde trait, that is R's way of specifying the model, which basically means that response is the output and it is approximately related to the input treatment. It is only approximate because of the presence of noise in the real life data. And data equal to nematode means the variables response and trait are coming from that data set. Incidentally, for this particular example, you can actually omit the first lines, not the first line, you can actually omit the third line and also can omit data equal to nematode from the fourth line. Okay. So, now that we have carried out analysis of, it is time to perform Tukey HSD on its output. Once we do that, that is, we pass ANOVA to the function Tukey HSD, we get a rather longish type of output, which starts with the heading Tukey multiple comparisons of means 95% family-wise confidence level. Now, it says that how to compare all the possible pairs. Remember, the different groups are called 0, 1000, 5000 and 10,000. So, the very first line compares the 1000 group with the 0 group. The difference turns out to be minus 0.225 and it creates an adjusted p-value. If a p-value is less than 0.05, in that case, that means the contrast is significant. Of course, this 0.05 is just a rule of thumb. In our case, I find that the first line shows a very high p-value, which means it is insignificant. Second line shows a p-value 0.0040599, much less than 0.05 cutoff. So, the 10,000 group differs significantly from the 0 group. Same is true about the next line. 5,000 group also differs significantly from the 0 group. The 10,000 group differs significantly from the 1,000 group, and the 5,000 differs significantly from the 10,000 group, but the 5,000 and 10,000 groups do not differ significantly. What does that mean? That means that 0 and the 1,000 groups, they form one bunch. The 5,000 and the 10,000 groups, they form another bunch. So, these two bunches are actually quite far apart. but inside each bunch the groups are essentially identical. We get this picture by looking at just the p-values. Of course, sometimes you are not just interested in the p-values, you also want to have an idea as to how much the group means differ. That is given by the confidence interval in columns 3 and 4, headed by LWR and UPR. LWR means the lower end and UPR means the upper end. Obviously, the entries in these columns will be useful when the p-values are less than 0.05, as in case of the second line. For example, I can see that the difference between the 10,000 group and the 0 group lies between minus 8.698577 to minus 1.701423. So, that is the basic interpretation of the Tukey HSD output. Now, if we wish to test any other contrast, we can do so writing the R codes accordingly to construct the contrast. So, in case of Tukey HSD, we are comparing all the pairwise contrasts. We do not have any control on which contrast we want to see. We have to look at all of them, and each contrast will consist of only 2 groups. But it may happen that we are interested in a contrast involving 3 groups. Then we have to specifically tell R about that. And this is done by creating the contrast matrix. So, what we do is we create a contrast matrix and assign that to contrast treat. This sets the contrast matrix for the treatments, and then I use the function summary.lm to the output returned by AOV. So, I use summary.lm applied to AOV of that particular formula. In this case, you get first the residuals, a 5-point summary of the residuals consisting of the minimum, first quartile, median, third quartile and the maximum, and the usual coefficients of the various terms. The intercept term is reported first with the estimate, its standard error, its t-value as well as the p-value. So, usually the first thing that we look at is the p-value. If the p-value is significant as measured by its magnitude or by the number of stars printed at the end of the line, only then we care to look at the estimate value and its standard error. The t-value is rarely of any practical use except to compute the last column. So, it is more like an internal step printed for the sake of completeness. In this case, treatment 1, which is the first contrast, that has an estimate 2.6187 with standard error 0.7216, and its p-value shows that it is significant. In fact, here all the effects are significant. I will draw your attention once more to the intercept row. Notice that it is written as 2.14 e minus 10. This means it is 2.14 times 10 to the power minus 10. So, it is very, very, very small, almost equal to 0. With this lecture, we come to the end of our discussion on analysis of variance using only one categorical input. This case is one of the simplest possible applications of linear models, and understanding this theory is really important in order to continue into the subsequent lectures, where we shall work with more than one categorical input.